Today in this video, I am going to explain the basic concept of a complex number. So now let's define the complex number first. A number which can be written in the form a plus iota b, where a and b are some real numbers and I, which is called iota, that is equal to under root minus 1. In the study of our complex numbers, under root minus 1 is denoted by I, that is called iota. So as I is equal to under root minus 1, iota square is equal to under root minus 1 whole square. Because of squaring, the root will be cancelled and you will get minus 1. So iota square is minus 1. Now iota cube may be written as iota square into iota, and as you know, iota square is equal to minus 1. So if we substitute minus 1 over here, we get minus iota and iota raised to the power 4, which may also be written as iota square whole square, that is minus 1 whole square, that is plus 1. So remember these four relation. Iota is equal to under root minus 1, iota square is equal to minus 1, iota cube is equal to minus iota, and iota raised to the power 4 is equal to 1. This is to remember. Now suppose we have to find out the value of a large power of iota, like iota raised to the power 492. So the easiest way to simplify this is to divide the power by 4 first. So first we have to divide 492 by 4. 4 ones are 4, 9, 4 twos are 8, subtract 1, 2, 4 threes are 12, subtract, we get 0 at last. So simply we may write iota raised to the power 492 as iota raised to the power 4 whole raised to the power 123, because as you see, on dividing 492 by 4 we get 0 at last. So 492 is the product of 4 and 123. So 492 in power may be written as iota raised to the power 4 raised to the power 123, because if you multiply 4 and 123 you will get again 492. So here we know iota raised to the power 4 is equal to 1. So if we replace iota raised to the power 4 here by 1, we have 1 raised to the power 123, and so ultimately we get 1. Iota raised to the power 492 is equal to 1. For better understanding, let's take one more example. Suppose we have to find the value of iota raised to the power 4573. 4573. Iota raised to the power 4573 we have to find out. So first we have to divide 4573 by 4. So one time, 4 ones are 4, subtract nil, take down 5, divide 5 by 4 one time, 4 ones are 4, subtract 1 left, take 7, 4 fours are 16, so we have 16 and 1 is left on subtracting, and take 3 down, we get 13, divide 13 by 4, 4 3s are 12, we may divide 13 by 4 3 times, and on subtracting we get 1 in the last. So as you know, by Euclidean division algorithm, 4573 may be written as 4 into 1143 plus 1. Dividend is equal to divisor multiplied by quotient plus remainder. So 4 into 1143 plus remainder is exactly equal to 4573. So ultimately, iota raised to the power 4573 may be written as iota raised to the power 4 multiplied by 1143 plus 1. By theory of indices, we may split these powers as iota raised to power 4 into 1143 multiplied by iota raised to the power 1, which is written iota simply. So here iota raised to power 4 into 1143 may be written as iota raised to the power 4 whole raised to the power 1143 into iota. As iota raised to power 4 is equal to 1, so we replace iota raised to power 4 by 1, we get 1 raised to the power 1143 into iota. 1 raised to the power anything is 1, so we get 1 into iota, and ultimately iota at last. So iota raised to power 4573 may be written as iota in the simplest form. Now let's come to the point. We were talking about complex number initially. So as we have defined a complex number, a number which may be written as a plus iota b is called a complex number, where a and b are real numbers and iota is equal to under root minus 1. So by the definition, we say a number which may be written. We don't say a number which is written in the form of a plus b iota, but we say a number which may be written. So let's talk about a real number like 3. 3 is a real number, or you may say a natural number or a whole number or an integer. So what about 3? Is it a complex number or not? So we say yes, it is a complex number because 3 may be written as 3 plus iota into 0. So ultimately iota into 0, 0, and you will get 3 plus 0, and 3 plus 0 is equal to 3. So 3 may be written as 3 plus iota 0, which is the form a plus iota b, as we have discussed that a and b are the real numbers, and you see 3 and 0 both are real numbers. So by the definition, 3 may also be written as 3 plus iota 0, which is the form a plus iota b. So we say that 3 is a complex number because it may be written in the form a plus iota b. So every real number, every natural number, every whole number, every integer is a complex number, but the converse is not true. That is, every complex number is not a real number or a natural number or an integer or a whole number. Suppose we write 2 plus 3 iota or 2 plus iota 3, which is a complex number, but It is neither a natural number nor a whole number nor an integer nor a real number. Now let's talk about complex number in details. Suppose a plus iota b is a complex number. A complex number is generally denoted by small z. The letter z is used to denote a complex number generally. So, suppose z is a complex number a plus iota b. Here, this part, that is a, is called real part of z, real part of complex number z, and b is called imaginary part. Imaginary part of z. In short, we write real part of z as re parenthesis z and imaginary part of z as im parenthesis z. So we say that if z is equal to a plus iota b, real part of z is equal to a and imaginary part of z is equal to b. Now let's talk about modulus of a complex number. What do we mean by modulus of a complex number? Let z is equal to x plus iota y is a complex number where x is the real part and y is the imaginary part. So the modulus of z, which is denoted by two vertical bars, z written within two vertical bars, which is read as modulus. So modulus z is equal to under root x square plus y square, or we may say that z modulus z is equal to under root real part square plus imaginary part square. So for example, z is equal to 2 plus 5 iota or 2 plus iota 5. So modulus of z is equal to under root 2 square plus 5 square is equal to under root 4 plus 25. That is equal to under root 29. So under root 29 is the modulus of the complex number. Now let's talk about argument of a complex number. So if z is equal to x plus iota y, argument of z, which is denoted by argz, is equal to tan inverse y upon x if x and y both are positive, and argument z is defined as pi minus tan inverse y upon x if x is negative and y is positive, and argument z is equal to pi plus tan inverse y upon x if x and y both are negative, and argument z is defined as 2 pi minus tan inverse y upon x if x is positive but y is negative. Or in this case, argument z is simply written as minus tan inverse y upon x. Now we will discuss the different values of argument for the different conditions. Basically, x plus iota y is plotted on a graph in such a way that x-axis is taken as a real axis and y-axis is taken as imaginary axis. So if we want to plot x plus iota y, we have to take a point whose perpendicular distance from the origin is x and perpendicular distance from the y-axis, parallel to y-axis from the origin is y. The perpendicular distance of the point parallel to x-axis from the origin is x and perpendicular distance parallel to y-axis from the origin is y. So it is written x plus iota y. So let it be point P. So if we join OP suppose OP makes an angle theta with x-axis. This theta angle is called argument of complex number x plus iota y. So if this is x, this is also x, obviously. So if we observe in this right angle triangle, tan theta is equal to perpendicular upon base, that is y upon x, and ultimately theta is equal to tan inverse y upon x. But this is when x plus iota y lies in the first quadrant, and as you see, all the distances on the right hand side along x-axis are taken positive and along y-axis above the origin are taken positive. So in the first quadrant, x and y both are positive. So we denote this situation as x comma y is greater than 0, which is our first condition. X comma y is greater than 0, then tan inverse y upon x is the argument of z. Now suppose x plus iota y is in the second quadrant, that is the real part is negative and imaginary part is positive. So if x is negative, it is taken on the left hand side of the origin, and y is taken positive because it is taken on above origin. So in the first quadrant, the case is x is negative and y is positive. Then suppose this angle is theta. So the angle made by the position vector of the point Q with the positive direction of x-axis, which is called argument of complex number, that is pi minus theta. If we subtract theta from this 180 degree, we get pi minus theta. So in this case, argument of z is equal to pi minus theta. And in this triangle, as you know, if the coordinate of this point is x and y, so this is the distance x and this is y, and as I said, x is negative, so arbitrarily we write x without negative sign, because already we have discussed that x is negative, because so it is taken on the left hand side of the origin. So in this triangle, tan theta is equal to perpendicular upon base, and this distance is obviously y. So by that figure we have tan theta is equal to y upon x, and theta is equal to tan inverse y upon x. So we have pi minus, and theta is equal to tan inverse y upon x, so we get tan inverse y upon x. So this is our second condition. Argument z is equal to pi minus tan inverse y upon x if x is negative and y is positive. And the third case is x and y both are negatives, and then argument z is taken as pi plus tan inverse y upon x, because if x and y both are negative, that means x plus I y lies in the third quadrant, and if it is in the third quadrant, let it be q dash x plus iota y, where x and y both are negative. So x and y both are negative in the third quadrant, and if we join O and q dash and drop a perpendicular from q to x axis. So let it be theta this time, and this distance must be y according to the coordinate of the point. So as you see, if we take the angle made by OQ dash with the positive direction of x-axis in clockwise direction, so it will be this angle, the angle from this line in clockwise direction up to x-axis, and obviously that will be 180 plus theta. So if x and y both are negative, argument z is equal to pi plus theta, and where theta is equal to tan inverse y upon x. So this is pi plus tan inverse y upon x. It was our third value, third condition of argument z, pi plus tan inverse y upon x if x and y both are negative. Similarly, we may understand the value of argument as 2 pi minus tan inverse y upon x when x is positive and y is negative, that is in the fourth quadrant. The case is 2 pi minus theta, and theta is tan inverse y upon x, so argument z is 2 pi minus tan inverse y upon x. And in the fourth quadrant, the case of minus theta is also applied, so 2 pi minus tan inverse y upon x may also be written as minus tan inverse y upon x. So this is all about argument of a complex number.